Hello and welcome to this Chemistry World webinar, Lead the Charge, Finding Modern Solutions for Lithium-ion Battery Material Characterization. I'm Philip Broadwith, Chemistry World's Business Editor. For those of you not familiar with GoToWebinar, it's an interactive platform, and one of the main advantages that we see is that you can ask questions of our speakers at any point. There is a box near the bottom of your GoToWebinar panel, default, that's on the right-hand side of your screen, for you to type in your questions, any that you may have. The questions are really important, so please do ask away. Don't wait until the end. If you miss any part of the presentation, or you just want to watch it back in your own time to pick up the details or any of the resources that we've sent out, we'll be sending a link to the recording in a couple of days' time. And to say thank you to everyone who's attended the webinar live, you'll get a certificate of attendance in that same email. Today's webinar is about using rheology and thermal analysis and calorimetry to understand the properties and processing of lithium-ion battery materials. Obviously, battery technology is hugely important for modern electronic devices, as well as for the transition to renewable energy. And understanding how to get the best performance out of battery technology is a crucial part of that. We'll cover some of the key rheological characteristics involved in developing processes to make reproducibly high-quality electrodes, as well as how thermal analysis can help select the right materials. We've worked with TA Instruments to bring you information that we think you'll be interested in, real experts in the field today. So to make sure everything runs smoothly and on time, we've pre-recorded today's presentations, but both of the speakers are here live in the webinar, and they'll be joining us for the live question and answer session at the end. They'll also be available to answer some of your questions in written form during the course of the webinar. So that's another reason to get your questions in nice and early. As soon as you think of them, just pop them in that Q&A box, and one of the speakers may be able to answer them straight away. We're going to be hearing later on from Marlene Surkursk, who is the product marketing specialist for isothermal calorimetry at TA Instruments, and she's considered the world's leading expert on the company's TAM isothermal instruments. Before that, we've got Hang Lao, who is the new marketing development scientific lead for lithium-ion batteries at TA. But first, it's time for the first of three quick polls that we're going to be running today. So I'll just ask Ben to launch the poll. So is battery recycling a concern for you? Please select one of the options. Yes, you're already working in battery recycling. Yes, you plan to be working in battery recycling. No, you're not concerned, or it's not applicable at all. We'll just leave that open for a little while to make sure that enough of you have voted, but it's going to be a quick one. Just a reminder for any of you who missed it at the start, you will get a link to the recording of the webinar in a couple of days' time, and a certificate of attendance in that same email. And again, the presenters are both going to be around. Okay, that's enough for that. I think we'll get the results of that poll. Looks like, yes, quite a lot of you planning to work in battery materials, so that would be quite useful for you to have this information. Okay, so I think it's time to get rid of that poll and time to launch into the first of our videos, which is from Hank.
Okay, thank you everyone. We're talking a topic for leading a change modern solution for battery material characterization. And my name is Hang Lao. And first of all, for battery, lithium-ion battery present a key technology to achieve a carbon neutralization footprint. And it will be facilitate a great electrification of a lot of the fields. So first of all, the consumer electronic, automobile, medical devices has been happen on a day-to-day basis. So what we all know, there's a 6 category of parameter that have been leading to change, advanced change in lithium-ion battery. First of all, is increasing runtime, improving a power outage of the battery, and hence safety, increasing electronic energy density, improve the cycle life of battery, and reduce costs. So it has been 6 parameters to get into getting into a better lithium-ion battery. So when we look at the workflow of lithium-ion battery, first of all, you will see a raw material characterization in the from mining and extracting raw material. And then those raw material active cathode and anode material will be go into formulation into battery material, including cathode, anode, separator, in electrolyte. So cathode material typically is by using a lithium metal oxide such as LFP, NMC, LCO, NCA, or LMO. And it will combine with a different binder, for example, PBF, PBDF. Anode material is typically have been used with graphite material, graphene, silicone, and it also will be combined with other active materials such as CMC and SBR. Separator a lot of times typically is made with polyethylene, polypropylene, or sometimes with a multi-layer structure to provide a better safety feature of the separator. Electrolyte a lot of time is being made with lithium salt and dissolved into organic carbonate solvent. And those organic carbonate solvent a lot of time will be used to enable the lithium ion mobilized between the cathode and anode material across the separator. So once you have all the four parameters of four active material in the battery, it will be formulated in different forms, cell shape. For example, a button cell, cylindrical, pouch cell, or parasitic cell as well. So by making those, as also after will be go into battery module. For example, in the EV market, it will also combine or add it into a battery thermal management system. It will be combining with different adhesive insulator to prevent thermal transfer between cell to cell or within the cell. And also include all other packaging material to package formula into a different module pack. So will be shipped to end use, such as in the automobile, consumer electronic, or a medical device. So after people have been used or the end you have been done, a lot of time you will be going to and you need a sustainable procedure for battery. It will be go back to recycling, and it will be involving a tear down of the battery. You're separating different material using the metal or different recycling processes to purify the material, and optimally it will be go back to the raw material in the supply chain. At last, you also will also see academic and government research into the battery material. The research will be also involving improving a new material, improving different electrochemical reaction. Also improving a different processing optimization to reduce costs during the battery production. Safety and next generation battery material also are important factor in here. And government also will, depending on different end use of the battery material, you will need to have a different regulation, make sure the safety and important of the battery performance. So first of all, I will go first into raw material, how our the technology able to characterize and study the raw material. So one example with the raw material is a lithium carbonate material. It's often used into a precursor of a cathode active material. One of the challenge there is you need to improve when you're making the cathode active material. A lot of time that you will be required to be able to improve the conversion and also a purity of the active material. And during the formulation or production process, high temperature singling process often involved in the production. And that will be, depends on the temperature, it will be very important, affecting the efficiency or the cycle performance on the cathode material. So one of the TA solution that we can give is the SDT can be able to measure the apparent melting and weight change at the same time in order to provide a good performance into the conversion. So if you look at the right graph, you can see that this is a figure of SDT mass specs. You can show that you see that the weight loss during the heated sinkling process, and in the same time that you was also measuring the heat flow signal. So you can see that in the melting, apparent melting of the lithium carbonate showing up in 724 degrees C, and that will be occurring at the same time that you see a degradation or conversion change into the lithium carbonate. And if you're coupling the SDT with a mass spec, you can also observe what type of off gas is coming off during the weight loss event as well. So in the figure, you can see that CO2, the mass to charge 44, is showing off. So we can see that CO2 is occurring during the heated sinkling process. By looking in the data, people can optimizing the sinkling process. So typically, sinkling process is between 725, where we're above the apparent melting temperature, to 880 degrees C. And when you're doing this characterization, you can able to improve the conversion and giving insight into the cathode material processing to obtain a higher purity of the material. SDT is, give you a little bit more background, is simultaneously DSC and TGA measure both heat flow and weight loss at the same time. It's able to measuring temperature up to 1500 degrees C. It will allow you to separating the endothermic and exothermic event, separating by different weight loss. So it can able to understand that either the heat flow event is because of melting or crystallization, which is typically no weight loss occurred, or is this due to the degradation of the material, which is oftentimes involving a weight loss event there. So there will give you a great advantage to measuring both signal at the same time. So when we have the active material, how are we making the electrode? So first of all, a lot of electrode manufacturing will be involved in a coating process. We'll be coating the electrode slurry material onto the collector, either the aluminum cathode collector or the copper anode collector. So the electrode slurry is mixed with either cathode or anode active material with different binder and additive into a solvent allowed it to make it to slurry material. After mixing together, it will go to, for example, a dissect clother to coat on the collector plate and involving a drying process. And first of all, the slurry performance is very important in order to get a uniform coating in the electrode. Shear viscosity on the slurry material is very critical or important into mixing, coating the slurry. And also the low shear rate viscosity is also important to predicting stability of the slurry performance. And in TA, the TA rheometer can able to measuring a different slurry viscosity in different shear rate. And in the figure on the right, you can see that there's a viscosity on the water-based anode slurry material. There's a two formulation there. One is with the natural graphite and the synthetic graphite. When you look at the high shear rate viscosity, it will give you an idea on how the slurry mixing and coating performance. So typically you will want to have a high shear rate viscosity in a lower value, viscosity value, which is able to better mixing and easier coating onto the collector. And when you look at the low shear rate viscosity, you typically want it to give it a high value. The high value will give you more stability and able to getting a better leveling after your coating process. To understanding both parameters can help you to reduce the manufacturing costs. And the other testing that you can see we use on the rheometer is the thixosophy testing. What it does is it will be going to give you a thixosophy index understanding how the difference between the high shear rate and low shear rate difference, and flexosopy recovery time. And it will be coming back to when you're looking into the recovery. So typically, the flexosopy measurement involves 3 steps. The first step is going to a low shear rate viscosity over time. That is mimicking the structure at rest behavior. And then the second step will go into a high shear rate measurement. And that will be demonstrating when the sturdy material get destructed, such as when you're doing the coating process. And the third process is you're going back to low shear rate and to mimicking after the coating process, how long it takes to observe the structural recovery of the sturdy material. And the flexosopy index is measuring by looking the difference between the low shear rate viscosity and the high shear rate viscosity we measure there. And the recovery time is looking at the change of the structure recovering. And after you're making the electrode, you dry it, you will also want to understand how well the coating process is. Is the electrode is going to be uniform over time? So in TGA, you can able to measuring the binder additive composition in the dry electrode. And in the example on the right is the anode electrode that contain a CMC and SBR content. By running in a TGA, you can see that looking for the degradation temperature of the CMC and SBR, and identifying the height, the weight loss from the CMC and SBR to characterizing the weight content of the CMC and SBR on the electrode. It allows you to be a quick QC check for the dry electrode, able to give you an idea on how the coating process is uniform over batch to batch. And those can be done in TGA or SDT. TGA will be giving you both binder additive content and active material content. And SDT, you can go up to 1500 degrees, give you a more idea on the active material stability as well. So TGA give you a little bit background on the TGA is actually measuring weight loss or weight gain in the material or in a function of time, temperature, or you can also do under different atmosphere pressure, different environment, such as nitrogen, argon, or air, oxygen. It allows you to measuring a thermal stability of the material. If you're switching the gas to oxygen or air, you can also understanding oxidative stability of the material. As the example I show you here with the SBR, CMC and SBR content, you can understanding the composition of multi-component system. Using a degradation study, you can also predict a lifetime of product, how long it takes to the material degrade. You can also measure the composition kinetic under different temperature or different heating rate. Volatile or moisture content, you can also measure under TGA as well. With the inorganic content, residue can give you an idea on how much inorganic content in the TGA. And another important component in the battery is the separator. Separator is made with a poor thin film polymer. A lot of time it made with polypropylene and polyethylene, or sometimes with a tri-layer of those. It is important to the separator is separating between the cathode and anode electrode to prevent the short circuit. But it requires a pore structure to allow lithium-ion to flow through. And it's very important for the battery safety, especially the mechanical integrity of the separator material. One of the important characterization of separator is involving measuring the thermal shrinkage of the separator and the melting integrity of the separator to prevent the failure during the operation of battery. So in TA instrument, the TMA allows you to measure deformation and the rupture temperature of the separator. If you're looking on the right figure, there's a TMA graph of the separator material that running into two different directions. So the machine direction in X and the Y direction. So you can see that in the X direction or the machine direction, oftentimes that when you lower in the tensile format, when you heat it in temperature until a certain temperature, you will see a thermal shrinkage. That is due to the manufacturing or processing of the separator thin film. So understanding the shrinkage temperature as well as how much is shrink, it will be important to predicting what's optimum operation temperature of the battery. Which you do not want the separator shrink too much to induce additional stress or reducing the thermal stability on the separator during the operation. It's very important to predict, help to predict the failure and improve the battery safety. In addition to TMA, DSC also allows you to measuring the melting temperature of the separator. You do not want to run it above the melting temperature of the separator to prevent maintaining the mechanical integrity. And DMA also allows you to measuring the mechanical property of a separator over different temperature range as well. And if we were looking more detail on the TMA allows you not only measuring the shrinkage, measuring the dimension change over different force. You can also control different atmosphere, time, and temperature. It allows you to measuring thermal expansion or shrinkage of different material. You can see thermal mechanical property change sometimes will be depending on mechanical structure, involving different chemical or physical change of the material. Linear coefficient of thermal expansion, we oftentimes call CTE, is another characterization for looking on different mechanical thermal stability, thermal expansion. You can also understand the phase transition of the material. Oftentimes, the phase transition involving change on thermal expansion, and you can able to measure those as well. Shrinking and contraction, that is important, and also if you have a different material combined together with very different of thermal expansion coefficient, you oftentimes will see delamination. So if you have those, you can also measure in the TMA. And with the TMA, we mentioned on the separator, we're using a tensile or thin fiber probe, but you also can use a TMA with different material structure, and we have a wide variety of probe selection here. And the fourth component that in the battery material is the electrolyte. Electrolyte is pretty much will be the core of the lithium-ion flow through between the cathode and anode, and is often involving dissolving a lithium salt into organic carbonate solvent. Due to the high reactivity of the lithium salt and high flammable of the organic solvent, is very important to understanding the decomposition and when the decomposition occurs and how much energy involved. Because of electrolyte decomposition often involve a very high exothermic reaction. And DSC allow us to measuring the both on-site temperature, which is when the thermal decomposition occurs, and also how much energy involved from the heat-off reaction. It can allow you to prevent the thermal runaway of the battery material and improve the battery safety. And then on the right figure, you can see the DSC electrode material that have been encapsulated into sealed high pressure capsule and running on the DSC. And you can see that the onset temperature where the reaction is starting to occur, roughly around 236 degrees C. And the heat of reaction generally is 345 joule per gram. And that is important for the understanding the onset temperature to prevent thermal runaway, And also the heat of reaction allowed you to design a certain battery thermal management system to prevent the battery cell propagate through to other cells as well. At the same time that you, with the TGA or EGA analysis, also allowed you to measuring the degradation temperature and also understanding what the composition of gases coming off that will be involving in battery safety. You may also want to, for electrical characterization, you will also want to measuring the viscosity on the electro material. A lot of time when the cell manufacturing, it will be sandwiched between cathode, separator, and the electrolyte oftentimes will be filled into the gap at the last. And understanding flowability of the electrolyte will be important during the cell manufacturing process as well. A little bit more detail on the DSC. So that we have shown a discovery series DSCs here. DSC is a measuring both heat flow different between the inner reference cell and also the sample cell in the function of time and temperature. In addition to the thermal runaway array characterization of the battery material, DSC also allowed you measuring different heat flow property, such as thermal transition temperature, specific heat capacity, and the heat of reaction or chemical reaction occurring. It also allowed you to measuring different exothermic event. So when you look into more detail on the heat flow equation, so the DSC actually measuring both the heat capacity, we call it heat capacity baseline, typically is heat capacity material, and it will be related to the heating rate. And the last step, the second is any kinetic event occurring into DSC. And with the modular DSC, you can also able to separate between the heat capacity event and any other kinetic event. So allowed you to do a much more accurate heat capacity measurement. So after you understanding a lot of heat flow signal, such as the heat capacity, you want to also making into the different cells. And people also need to understanding the heat parameter to designing the battery thermal management system. So that is a couple battery management systems that have been in the market. For example, would be using air to cool the battery cell. There's other using a liquid, high thermal conductivity liquid to cooling the battery module. And also more commonly now people using in a phase change material, we call it PCMs, to use the heat flow signal to use the change of the heat flow during the different phase transition, enable to reduce or recooling the battery or maintain the stable temperature. The thermal management system can be used all three different parameters, and want to give you a little more detail onto the phase change material, how it's actually used and how to maintain the battery temperature. So the challenge in here is maintaining the temperature within the cell and also between from cell to cell to prevent any heat flow change to give a better battery performance. And the phase change material will be under different phase transition. So in the figure on the right, you can see that there's one phase change material, paraffin wax. It will be undergo a solid-solid phase transition around 34 degrees C, and then a solid liquid phase transition during a 52 or 53 degrees C. And by looking on the phase change, and you can see that it will be an endothermic event. It will be remove heat from any during the battery thermal management system. So to understanding the amount of heat that it can, or what type of temperature that this phase change event occur, DSCA and allow you to measure those. So as I mentioned, you can see that the solid-solid phase transition occurring, and all the total heat flow or total enthalpy involved in this process is 202 joule per gram. And those is how much amount of heat that able to remove from the battery during the battery management system. And it will be allowed you to, with the different parameter setting, you can allow you to improve the battery's safety and use it to predict how the battery performance as well. In addition to DSC, to understanding those phase change material, flash system, we call it thermal diffusivity measurement, will be allowed you to understanding how fast this heat transfer of this thermal change material or other type of material to predict or designing a better thermal management system. In addition to that, TGA, to understanding what is the thermal stability of this PCA material, will be important to make sure that it's designed to not go above the degradation of the phase change material. I mentioned a flash system previously, so it's measuring a thermal diffusivity, how fast the heat flow across changing into the material. And one of the challenges to measuring the thermal conductivity into a highly conductive material is because if the conductivity is too fast, it's difficult to measure. And the flash system is allowed to measuring the thermal diffusivity of the high thermal conductive material. And one of the examples I'm showing here is the copper thin film. This is an example of 25 micron thin film material that we can able measuring the thermal diffusivity using a through plane. So it allows you to give you provide you to go through a sample and the mask to prevent the heat flow go directly. And by looking into the heat flow change on the thermocouple on the backside of the sample, allows you to feed into the solution to measuring thermal diffusivity of the copper thin film. And the thermal diffusivity, you can measure it here, is 1.17 centimeters square per second. And it can very easier to relate it back to thermal conductivity. It's just the ratio between the density of the material and the heat capacity. And the specific heat capacity you can also measure with a DSC. And allowing to measuring the thermal diffusivity allows you to better designing your battery management system. And last but not least, you also have a solution to measuring the battery full cell. Once you're making into the full cell category with different form factor, understanding the battery performance and predict the lifetime is important. And our TEM system allows you to measuring those in a non-destructive way. You can measuring the electrochemical reaction during the process, and allow you to measuring the peristaltic reaction, heat flow change, and charge and discharge during the charge and discharge. And Marlene will be giving you a little bit more detail on the TEM system and how to apply to the battery cell testing.
Okay, so that's the end of the first video. We've got another quick poll now, so I'll just ask Ben to launch that for us. And do remember that while the poll is going, you can still answer your questions. So do you need to use your instruments inside?
So I will be talking about calorimetry and battery.
Oh, hang on. Do you need to use your instruments inside a glove box? If so, which ones? So you can select multiple answers on this, any and all that apply from TGA, thermogravimetric analysis, DSC, differential scanning calorimetry, rheometry. Somewhere nearby to a fume hood is good enough, don't need to be inside it, or it's just not applicable at all. So we'll just give you a little while to get some votes in. To remember, you can submit your questions at any time. I can see that Hang and Marlon and Chris have been very busy answering several of your questions already, but do keep them coming in so that we've got some more to ask in the question and answer session at the end. And remember that you will get access to a recording and a certificate of attendance in an email a little while after the event has finished. So I think we're just about there with the votes. So I'll just get Ben to close that down and we'll have a quick look at the results. That's a good mix. I think, fairly even. So that's very useful. Obviously, all of this information is useful to all of you, so that's quite good. Okay, I think we're just going to go into the next presentation video now from Marlin Sukursk.
Okay, so I will be talking about calorimetry and battery testing. Many of you may have heard about calorimetry, but then maybe it's about adiabatic calorimetry or accelerated rate calorimetry for doing battery safety testing or thermal runaway testing. And we just heard about DSC, scanning calorimetry, but I will focus only on isothermal microcalorimetry, could be abbreviated IMC, or also called heat flow calorimetry, HFC, for today. And with microcalorimetry, you can study whole batteries as well as battery components to evaluate battery performance and parasitic reactions. So isothermal microcalorimetry is a technique that measures the heat produced or consumed during a physical process or chemical reactions in terms of heat flow at a constant temperature with microwatt sensitivity or better. If we look at the graph here, the blue curve, that's the heat flow data, normalized heat flow data in this case, and it's a direct measure of the intensity of the process under study or the processes, because we will measure everything that goes on in the sample. So the intensity then relates to the reaction rate times the enthalpy of the reaction or the reactions. If we integrate the heat flow, we will get the heat, which is the green graph here. And the heat is a measure of the extent of the process. And if we let the reaction go to completion, we get the enthalpy of the reaction or the total apparent enthalpy of the process you are studying. So the microcalorimeter we use, it's called TAM, so you have the thermal activity monitor. And the TAM can be used for battery testing, where we can do testing in situ or apparando for looking at performance. We can do lifetime predictions or determine different parameters for safety assessment. So TAM could, on whole cells, evaluate and understand parasitic reactions, look at lithium plating reactions, rank cells with different additives, get your data for thermal management, and as a general battery design or battery chemistry testing. As well as looking at whole battery, we can also look at battery components or individual components to characterize these properties. So we can do stability and compatibility, look at humidity sensitivity by changing the relative humidity over a sample, looking at sorption reactions, and material interactions within liquids or slurries as well. The TAM4 is a modular calorimeter system, and the base is the thermostat. So this is what we see in the picture in the middle. This is a thermostat that could control the temperature very well for our isothermal measurements. It will have 4 positions. These positions can be equipped with from 1 up to 4 different calorimeters, depending on what type of samples you want to study or what sensitivity or throughput is needed. So you will put the calorimeter, like this one is the one that's shown here. It will be immersed in the thermostat liquid. To hold the battery or the battery components, we have sample handling systems. We also refer to them as ampules. Like in the picture here, we don't see it, but this is holding a coin cell inside. It could also hold like a wrapped pouch cell, and it could be wired so we can do charge discharging inside the calorimeter. There is also different auxiliary equipment, like here we can collect voltage signal at the same time you are collecting the heat flow data from your battery. Different battery types and different sizes, and if you need higher throughput or higher sensitivity, there are different type of calorimeters you can equip the thermostat with. We can have both cylindrical up to, like in this calorimeter here, which is the most sensitive, for up to 18650 batteries. diesel size type of batteries, and smaller batteries in the 20 milliliter calorimeters. This will offer a higher throughput where you can do up to 12 parallel samples at a time. And depending on the sensitivity of the calorimeter, you can do self-discharge of battery, but you can also do charge-discharge, and we can do heat capacity measurements on whole batteries by stepping the temperature. Parasitic cell reactions, they are shown to be strongly related to battery lifetime. And isothermal microcalorimetry is a very good method to actually look at these parasitic reactions, because we can separate the reactions that comes from charging a battery from the parasitic reactions, which I will show later. So we can study the parasitic cell reactions and we can see them, and we can study how additives will change or minimize the parasitic reactions. So we can use IMC to predict battery performance and lifetime by addressing the parasitic reactions. We can use IMC as a guide or a help to choose what electrolyte design you should have and how to optimize that for increased lifetime. It could also be used to determine optimal voltage ranges and determine the voltage cutoff. So how do we measure this? Or when we measure the heat flow or the thermal power from a battery when a current is passed through the cell, we are measuring, as I mentioned, the whole reaction that goes on in the battery. So the total heat flow, we denote that P. This can be divided into the polarization heat, which is exothermic and it's current dependent. We have the entropy changes. This is also called the reversible heating. It's the configurational changes due to intercalation. They are reversible and they are current independent. And then the last term, the parasitic reactions, which are not part of the battery chemistry and can lead to a loss of capacity for the battery. This can be due to oxidation, material incompatibilities, and formation of passivation layers. These reactions also typically decay with time or charge cycles. We can see in the graph here, we have the blue curve, that's the voltage, the charge-discharge. And we can see the red, which is the battery heat flow that is then composed of all these different reactions. Quite complicated curve. There are different ways to access, so qualitatively or quantitatively, about the parasitic reactions. So you can evaluate the effect of adding different additives to minimize the parasitic reactions, as in this example where vinylene carbonate is added, and increasing amounts of vinylene carbonate is added, and we can then compare if everything else is equal with the batteries, the magnitude of the heat flow during the charge-discharge cycles can be compared. Looking at the voltage for the charge-discharge, the voltage is no difference, but we can see there are quite a bit of difference between the green, which is 4% additive, and the black curve that is the control where there is no additive at all. And we can see that the control has a higher heat flow than the one with the additive at all times, which indicates there are more parasitic reactions. Also, if it's first cycle and then left at open circuit conditions, it could also be followed over time, the decay. And when you have no current passing through, what you will see is only the parasitic reactions when you're looking at them. And again, it's quite a big difference between the control with no additives and the one with the most additive. It could then, as mentioned, be used to rank cells, rank between different additives, and also choose how much additive is needed. After 2%, the improvement is not that much, so maybe it's enough to do a 2% additive to this particular battery. Then there is a method to separate the heat flow components as well, which is called the integration subtraction method. So if you cycle discharge and charge over a full cycle, do them the same and measure the heat flow at the same time. And we know that the entropy changes are reversible. So if we do a full cycle, in this case, the curve is now flipped over from the lower voltage here and integrate the area under the curves, the entropy changes will cancel out because they are reversible on discharge and charge. And then we are left with the polarization heat and the parasitic heat. If the voltage is measured simultaneously, the voltage hysteresis can also be integrated, and that's the heat of polarization. So if we subtract the heat of polarization from the total where we have integrated, cancel out that, and subtract away the polarization heat, we are left with how much of parasitic heat that is produced from this battery. This has been developed by Larry Krauss and Jeff Dahn and co-workers, this method. So that was for looking at lifetime and parasitic reactions, but we can also increase the battery knowledge in general by measuring, evaluate the batteries in situ or operando in the TAM. There are examples where you can study the lithium plating effect, where you see not very much on the voltage curve, but you can see effects in the heat flow data. Material phase changes, if there is a crystallization that occurs at some part of the charge-discharge cycle. It could be used to look at battery safety and thermal management. As mentioned, we can measure heat capacity of battery, which is important. It is possible to determine the current independent enthalpy potential for battery heat production. So even if we do charge-discharging very slow in TAM, since it's the enthalpy potential is current independent, this value can be used to calculate if you will do much faster charging or discharging. And it could be used as a general tool to reveal cell design issues and if there is any material incompatibilities. Calorimetry or isothermal microcalorimetry is also used for quality control, especially for looking at implantable medical device batteries. So this example of lithium plating, where we have in the panel here, the first panel, the battery is charged and discharged under non-plating conditions, and in this panel, it's under plating conditions. If we just zoom in on the top part here, what you see here, we can see there is no events more than the heat flow and the voltage. There is nothing else seen. In the under plating conditions, you don't see very much on the voltage signal, but we do detect an event in the heat flow when this lithium plating has occurred. And then heat capacity is important. We just heard that you can do specific heat capacity measurements on individual materials, but in the TAM, you can also measure the heat capacity of the whole battery. In many cases, you will calculate the battery heat capacity from the ingoing material, but it's also possible to measure this by doing the step isothermal method. In this case, we will cycle the temperature of the calorimeter in a small range, in this case between 25 degrees. We will measure how much heat that is needed to heat or cool the battery, and then we can divide that by the temperature step. We do need to do blank measurements of this because we need to know the heat capacity of the sample holder and the ampule. We also recommend to calibrate with a well-defined substance like sapphire, so we know what heat capacity we should get, and then you can do this test with the battery itself. And here was an example of a coin cell that was measured in the TAM. And this could be programmed to be done stepwise at higher and higher temperature to see how the heat capacity is changing. So implantable medical devices have, like pacemakers, defibrillators, or neurostimulators, are using batteries, in many cases non-rechargeable batteries, but the battery performance and the lifetime reliability are extremely important for these devices. There are examples where microcalorimetry is used to study like a quality control of the battery. In many cases, the whole device, like the whole pacemaker, is put into the calorimeter. They are expected, if there is no operation of the system or they are passive, they should generate a small amount of heat between 1 and 20 microwatt, and more likely they will be below 10 microwatt of heat. And this is an example. This is a pure coin cell, and this is a pacemaker device battery. If there will be a failure in the battery, they would typically generate a lot more heat. So this was for the full cell battery testing. We also offer different type of accessories that could be manipulating the sample over the measurement. What I have mentioned now is the ampule calorimetry. We put the whole battery or the individual components. Maybe we would do charge discharging or measure the voltage, but otherwise we do nothing with the battery. It's possible to do titration calorimetry, where you have a slurry or you have a solution of one component and you can inject another component and measure the heat of reaction when they react between each other. Or you can wet the powder, measure the heat of wetting with titration calorimetry. Perfusion calorimetry will offer possibilities for maybe an individual material to change the atmosphere between gases, study oxidation, or change the conditions above the sample to study specific reactions. RH perfusion calorimetry is a special version of the perfusion calorimetry. Here we can change the relative humidity over a sample, measure sorption, desorption, if we initiate a reaction with humidity, or any other a vapor activity from a solvent as well is also possible. Pressure calorimetry, where we can measure the pressure evolved at the same time as we measure the heat flow. And solution calorimetry, where we can dissolve a sample or wet the sample in a bulk liquid to measure heat of wetting or heat of dissolution. So just to show an example of battery component testing, we measure stability and compatibility, and then we have a curve here where we measure the heat flow of one non-coated electrode and a coated electrode. We can put the whole assembly or the sample only into the calorimeter. Typically, it's done under slightly elevated conditions between 40 and 60 degrees maybe, so we accelerate the reaction. And we can see that the coated electrode in this case would be more stable than the non-coated electrode. I already mentioned humidity sensitivity and sorption, gas release and pressure increase, and interactions and complexations of battery components. So to summarize the isothermal microcalorimetry section, calorimetry is the only method that can directly measure the occurrence of non-current producing reactions under load. It is highly sensitive, it is non-destructive, simple and continuous, and it could be used for a wide variety of applications for increased battery understanding, as whole cell battery testing, predict battery lifetime, screen battery chemistry, evaluate parasitic reactions. To evaluate electrolyte chemistry, you can rank the effect of the additives. You can study the electrolyte electrode compatibility, looking at material evaluations. And in many cases, I didn't mention that before, it's done also in model batteries. Even if you can't fit the big batteries, you can do smaller batteries to evaluate chemistry, additives, electrolyte, and electrode materials in model batteries like coin or pouch cells. Then you can study material incompatibility, lithium plating, phase changes, and also get data for battery safety to model cell the thermal output and to measure the heat capacity. And from here, I will leave the word back to Hang to summarize the whole presentation.
Thank you, Marlene. So hopefully we've give a brief overview on the battery material characterization solution that offered by TA Instrument. And I hope we have shown you guys on the different active materials such cathode, anode, separator, electrolyte characterization using one of our TA Instrument. We're also demonstrating some of the electrode manufacturing, how the rheometer and TAG are able to enhance the manufacturing of the cathode material as well as using it for quality control purposes. Also improving a battery safety and thermal management system in the separator characterization as well as the thermal management system. And understanding the battery lifetime and predicting the performance using our TAM system. And that's a whole range of material characterization solution that TA Instrument offer.
Okay, so that's the end of our 2 video presentations. We've got one final quick poll, which I'll just get Ben to launch now, which is from an analysis perspective, which part of the battery is the greatest concern? You can select multiple options on this, just select all of the ones that apply. Is it the cathode, the anode, separator, the electrolyte or additives, or the whole cell that you'd like to analyze most likely? So in a moment, we're going to be going through to the live Q&A session. As I can see, lots of your questions have been answered already by our speakers, but there are still a few coming through. We've got some really good questions lined up as well. So do keep putting your questions into that questions box. Quick reminder that you will get the recording and certificate of attendance when you within a couple of days of the presentation. Okay, we're getting up towards an indicative vote there, and I want to preserve some time for Q&A, so I'll ask Ben to finish the vote at that point. Again, looks like a good spread of applications. So I mean that's showing that that most of this presentation has been useful in some aspect to good chunks of our audience. So that's really good. Okay, so let's finish that and we'll go over to the live Q&A. So I'll just ask Hang and Marlon to join me on camera and make sure we can hear you both. Hi, Hang.
Hi, Philip.
Thanks for joining us. And Marlon, you're looking good there as well. Great. Okay, so I think I'll kick off straight away with the first question, which is to Hang, and it comes from Anjali. She's asking about the effect of phase changes in TMA, thermomechanical analysis. What, because you were talking about phase change materials, what's the effect of a phase change in TMA?
So, for example, if it's a lot of time that for TMA, we're looking on the thermal expansion under different phase transition. For example, if a polymer under glass transition, there would be differences. Below the glass transition, the thermal expansion, because this was all solid glassy state, the thermal expansion is much smaller comparing to after a glass transition going to above the glass transition. The material will be expand more. So the thermal expansion coefficient will be different between you below the glass transition and above the glass transition. And the TMA allow you to measure those differences and identify the type of phase transition. So depends on the type of transition, you will see a slightly difference on the thermal expansion. Brilliant.
Okay, thanks very much. I'm sure that answers that very nicely. So next question is to Marlon, and that's from Nicholas. What's the maximum dimension that you can measure in the system you were talking about? So, for example, what's the biggest pouch cell that size you can say? Towards the end of your presentation, you said maybe you won't be able to fit the biggest batteries in there. What's the biggest size you can fit in?
Yeah, most sizes will be model system. The biggest size pouch cell we could do is about 11 centimeters times 6. So 11 times 6 will get into a calorimeter. And that's for the biggest calorimeter we have. If you would do more smaller model pouch, you can also fit them into the 20 milliliter. Then they would be like some model pouch systems would be 2.5 times 2 centimeters, and they could be rolled into that 20 milliliter calorimeter.
Okay, thanks very much. That big one's quite pretty big then. You can get some fairly decent sized stuff in there.
Yeah.
Great. Okay, so let's have a couple of other questions. I think so. To Hang, how do you use? In fact, actually, we could ask this question to both Hang and Martin, because both of you mentioned measuring heat capacities. So Hang, can you give us just a bit of a brief description about how you measure those heat capacities in DSC? And then Marlon, can you just explain, you had a slide measuring heat capacity using the technique you were talking about as well.
Sure. So if I can share a slide on one of the. So we're looking at the heat flow data on the DSC data. We are measuring the heat flow. The heat flow signal is related to the heat capacity multiplied by the heating rate, and with any kinetic event. So for when you're measuring the heat capacity, there's no phase transition occurring and no any kinetic event. You can simply divide that by calculating heat capacity would be the heat flow measurement divided by the heating rate multiplied by a calibration constant that typically is used. Sci-fi material have a known heat capacity material that use it to calibrate a calibration constant there. And then you can measuring that, plug it back together and get your heat capacity of your material. There's multiple techniques that you can do. There's the ASTM method. There's also a direct heat capacity measurement that you can do with the 2500 Discovery DSC. And you can also use a moderate DSC function to do measuring the heat capacity on any DSC that have moderate DSC option.
Brilliant, thanks Hang. And Marlon?
And then I can go back. Okay, but go back to the moon.
Yeah, okay.
Yeah, that's the one.
Yeah, so what we do in the microcalorimeter, I didn't mention how calorimetry works, but it's a sample and reference side. So when we change the temperature of the calorimeter, heat will flow in if we increase the temperature, and we will see how much heat that is needed to heat up the battery 1 degree in this case, because I jumped it 1 degree at a time. So we get a heat flow curve, and we can integrate that for that temperature step. If we have done a blank, we have the blank heat, and then we subtract away that from how much heat is needed to heat up a battery, for example, and then we divide it, just the area under the curve divided by the temperature step and maybe weight, or in this case, this example was a coin cell, so we normalized it per cell only. So, but how much heat is needed or needs to be removed in relative to the reference in the calorimeter to heat up the battery.
Okay, great. I think that's really nice. And I think we've probably got time for one more question each, because we're just slightly over time. Marlon, can you give us a bit of an idea about how to select what kind of instrument, what kind of isothermal microcalorimeter is the best option for a particular experiment? And maybe Hang, you can give us some information about some of the techniques you were talking about and where people can get more information about which will be the best for certain applications.
Okay, so if I just start for the microcalorimetry part, so we have different type of calorimeters that will fit different sizes and have different sensitivity. For screening parasitic reactions, for example, you would like to have more calorimeters. So then that 20 milliliter with higher throughput, you can get up to 12 at a time. But in many cases, you will need to do model system to test the different chemistries you do. But then you get throughput. If you need very high sensitivity, you can choose other calorimeters. For example, medical device, implantable medical devices, where you need to measure at a very high sensitivity, then you might want to have another type of calorimeter. So it will always depend on the sensitivity and the throughput you would need for that.
Great, thanks. And Hang?
So we can have a lot of webinar and training interview that on the TA Instrument website. You can also go to our TA Instrument website, that the link that provide in the screen right now. This TA Instrument, the battery website, to get a little bit more information on specific product that we mentioned about. And with selecting the instrument, it would depends on what you're measuring for and the temperature range that you're measuring. So if you have any inquiry, you can reach out to us, and then we can help you to identify a specific model for you for fitting your application.
Okay, great. I think we'll bring it to a close there. I know we've had a lot more kind of specific technical questions, which Hang and Mylon have done a fantastic job, and Chris have done a great job of answering during the course of the webinar. So I'm really glad to see there's been some really good questions there. But it's just to relate to thank Hang and Mylon again for their presentations. Absolutely fascinating. Thanks to TA Instruments for sponsoring the webinar. There have been a couple of web URLs, including that one on the screen, that have gone out in the chat. If you want to save those to look at later, then do grab them now, because you will lose them once we close the webinar. You'll have to rewatch to get back to them. So do grab them now before the webinar ends. Thanks all of you in the audience for attending. This is, the most important aspect is, the reason we do this is to get information from our experts to you. So thank you for your attendance and for your engagement during the course of the day. If you liked this webinar, then do check out chemistryworld.com/webinars to see what other topics are coming up. And I hope to see you in another Chemistry World webinar very soon. I'm Philip Broadwith, and I'm Chemistry World's business editor. Goodbye.